We are together again, guys. Pretty excited about that. Alright, well, we got basics of vectors going on still. Long section. I told you that in the first video for this section. And we're actually going to accomplish two goals here because they're both pretty simple. The first is that you're going to find and use a position vector for a point in the coordinate plane. And the second, which is the fifth overall for this section, is that you will find and use a resultant vector between 2 points. So if I was going to kind of summarize really quickly what we're trying to distinguish between here, what we're trying to learn and then distinguish between, I need you to know what a position vector is. I need you to know what a resultant vector is and what the difference between the two is as well. Then the problems that we're going to do, well, they'll kind of be related to those definitions, but they're just kind of good vector problems altogether, it turns out. Well, let's talk about what those words mean. I've got a diagram here where I've got a couple of position vectors drawn, and I've got a resultant vector drawn as well. Now, a position vector basically is this. It's a vector that tells you how to get from the origin to a point. Now, I already told you that we have two position vectors here, one of them being the vector from O to point A. We're always going to call the origin O. Whenever you see vector O something, just assume that it's a position vector. And we've got the position vector from O to B. And if you're ever wanting to find out what the component form in either form that we write it in for a position vector is, you just have to know what the coordinates of the point are that you're getting to from the origin. So you can see the coordinates of A and B are as I've labeled now. And then the position vectors that correspond with those, well, for position vector OA, it would be 8, 3. Make sure you never write vector as an ordered pair and never write an ordered pair as a vector. All right, and then for vector OB, 5, 10 is the position vector. It's column form. Okay, now a position vector goes from an origin to a point. Another term that you need to know that I mentioned earlier is a resultant vector. And a resultant vector goes from one point that's not the origin to another point that's not the origin. Well, it doesn't have to be not the origin, but from one point to another. Which in this case would make ray AB, well, vector AB, a resultant vector. Now there's a relationship I want you to know between position vectors and resultant vectors, although I don't use it in practice too often. Still, it's kind of a cool thing. You can always use the position vectors for 2 points in order to figure out what the resultant vector that would get you from one point to the other would be. Aren't there two ways that I could get from point A to B here using line segments, for lack of a better term, that I've drawn on the diagram? I could either go directly from A to B, or I could go from A back to the origin and then back to B. And if I do that, I could utilize the position vectors in order to figure out what AB equals. Now I'm going to write an equation here and then show you how I don't really use it, but it makes sense to at least know it. Now I'm going to write this in a couple steps. First of all, if I want to find the vector from A to B, I could go from A back to the origin, plus I could go from the origin over to B. Now if I'd like to write that in terms of position vectors, which this is not because it doesn't start at the origin, that would look this way. Notice I switched the vector AO to the opposite of OA because they are opposites of one another. So I just put a negative sign there and then switch the order of their points. Yeah, so one thing you can do to find a resultant vector is you can subtract the position vector for the second point from, or minus the position vector of the first point. So position vector of B minus the position vector of A. Of course, what I prefer to do in practice is simply this. If I want to find a vector from A to B, and I already know the coordinates of those points, A and B, I'm just going to subtract the coordinates of B minus the coordinates of A. Like so. So subtract their x coordinates, subtract their y coordinates, and make sure you put B minus A, not A minus B if you're going from A to B. Always terminal point minus initial point. And in this case, it gives me 5 minus 8 is negative 3. And then 10 minus 3 is 7. So that tells me that to get from A to B, I would go left 3 units and up 7 units, and you can see that that works out quite nicely. Great. Well, let's work on some problems involving position vectors or resultant vectors or similar things anyway. Here I've given you a problem where I'm saying there's a point A that has this for a position vector, here's a position vector for point B, and here's a position vector for point C, and I want to figure out what these vectors would be in column vector form. Well, what I suggest is simply finding out, and there's not a lot to this, find out what the coordinates for points A, B, and C are, and then just subtract the coordinates the way that I showed you a moment ago to find out what these resultant vectors are. Because those are resultant vectors, right? It's from one point to another. It's not from the origin to a point. Go ahead and try it out real quick. Now you see I've written the coordinates for points A, B, and C down here at the bottom, just using the position vectors. You immediately know what the coordinates for each of those points are, because that's from how you get to the origin to each of those points, right? And then to find the component for the resultant vector AC, I'm going to subtract the coordinates of C minus the coordinates of A, and I'm going to write them as column vectors as instructed. And of course 3 minus 4 is negative 1, and negative 1 minus 1 is negative 2. Alright, make sure you're doing the terminal point minus the initial point for these resultant vectors. Then for vector CB, we're starting at C, we're ending at B, so we're going to do the coordinates of B minus the coordinates of C and get negative 5, 1. Negative 2 minus 3, 0 minus negative 1. Excellent. Now, one more problem in the textbook, they don't give you a picture for it. I'm going to talk this to you through pictures because it's not directly related to the position vectors that we were just learning. It says here that a vector DE is given by 2i minus 3j, so there's the unit vector form, and the vector EF is given by I plus 4j, and we're going to use that to find vector DF. Okay, now what I'm wanting you to notice here is this. These two vectors have a relationship. You start at D and end at E on one of them, and then you take that ending point, and that's the beginning point, or the initial point for the second vector. Now, it doesn't give you the position vectors for points D, E, or F, and what that means is that we can place these vectors anywhere the heck we want to in the coordinate plane. So I'm just going to pick a random point on my coordinate plane. I'm going to call it point D, and this is just to reason this out for you. So let's put point D right there. Now the vector from D to E goes 2 units to the right and then 3 units down. So I'm going to put point E 2 units to the right and 3 units below point D. And it's coincidental that those both ended up being intercepts. Don't even worry about that. The thing I'm trying to get across to you is put the initial point anywhere and then use the unit vector form to figure out where the next point for the vector is. All right, so there's vector DE. And then we're going to start at E, and we're going to go 1 unit right and 4 units up to get to F, as shown right there. Now, what we're really trying to do is figure out what is the resultant vector DF. How would you go directly from D to F? And I want you to see a really cool relationship here between these first two vectors and this one. And I'm about ready to show you that relationship, but let's not skip over the obvious. We can tell from our diagram that we made that if you go 3 units right and 1 unit up, you get straight from D to F. So 3i plus j would be the unit vector form of vector DF. But I wanted to show you the relationship between the two vectors I have in green and the one I have in orange, so let me show you that now. Notice if I take the other two vectors and just simply add their components together, 2i plus I gives me 3i, negative 3j plus 4j gives me j. That gives me the vector from D to F already. So if I want to find a vector from D to F, instead of going all the way from D to E and then E to F, just going from the first point to the last point, I could just add these other two vectors together and that'll work out for me. So the vector DF equals the sum of vectors DE and EF. It's a pretty good bit of knowledge to have in your arsenal. Thank you very much for watching again. We're not quite done with section 9.1 or 12.1, but we're getting there. See you next time.